Hello and welcome to the first video of the M3 chapter Dynamics. Quick question from M2 to review an idea here. A particle p moves along the x-axis. At time t seconds the velocity of p is v in the positive x direction, where v is a function of t given here. When t is equal to 0, p is at the origin O. Find the distance of p from O when p is moving with minimum velocity. To find the displacement, we can remember that dx by dt is equal to v, therefore the integral dx is equal to the integral v dt. So we can take this expression 3t squared minus 4t plus 3 and integrate it with respect to t to find x. That gives t cubed minus 2t squared plus 3t plus c is x. Using our boundary conditions, when t is 0, p is at the origin, so the x is 0. So when t is 0, x is 0, which means c is 0. So our expression for the displacement is this. Now to find the time we need to know when is p moving with minimum velocity. To find the minimum, we're going to differentiate the v expression to get a, set that equal to 0 to find the minimum point. So that's 6t minus 4. When this equals 0, we have our minimum or maximum. In this case, it is only one answer, so that will be the time for the minimum velocity. So we put this in here, and we get the displacement at that time. And if I put all that on my calculator, I get the answer 38/27, or 1.41 meters to 3 significant figures. A quick review of variable acceleration there, because we're going to be using that in this video. Quick overview of the chapter. We're going to be applying calculus, like we did there, to Newton's second law in a straight line. Now we'll use Newton's law of gravitation. Simple harmonic motion, we'll look at that in some depth, and then we'll apply that to horizontal oscillation problems and vertical oscillation problems. So these two here are slightly separate from these three. So in this video, we're just going to apply what we did there with variable acceleration to Newton's second law, F equals ma, to have variable force. So as we had there in kinematics, we used calculus for variable acceleration, which we can now connect with variable force through Newton's second law, F equals ma. But there were two different versions of acceleration that we can apply. We had this one that we've just used in the starter question, a equals dv by dt, but we also have a equals v dv by dx. So depending on your question, and you will have to decide for yourself which one of these is appropriate, you can choose to have v as a function of t or v as a function of x. Initially, it might seem that a lot of them have this, but as we get into simple harmonic motion, the usefulness of this one will become more apparent. That's it for the notes. All we're really doing is applying this work into this equation here. So a few examples. A particle p of mass 0.5 kilograms is moving along the x-axis. At time t seconds, the force acting on p has a magnitude this. So you can see we're being given a variable force as a function of time, and it acts in the direction OP. When t is 0, p is at rest and at O. Calculate these two things here. So if we need the speed of p when t is 2, we're going to need an expression for the velocity. So to start with, let's connect through F equals ma, the velocity and the variable force. On the left, we have 5t squared plus e to the 0.2t for the force. On the right, we have the mass, 0.5, and acceleration. Now, between my two acceleration options, I want dv by dt, because we want the speed, and we have force in terms of time. So if I write dv by dt, not v dv by dx, then I can separate the variables and integrate. So I have the integral of 5t squared plus e to the 0.2t dt is equal to the integral of 0.5 dv, 5 over 3 t cubed plus 5e 0.2t plus c is equal to 0.5 v. Now we go back to our boundary conditions. When t is equal to 0, p is at rest. So when t is 0, v is 0, but because of this exponent section here, that does not mean c is 0. When we put 0 in here, we get a 1 out of this exponent, so we have 5 plus c equals 0, so c here must equal minus 5. Because t equals 0, v equals 0 leads to this. So if I put that in and I rearrange to make v the subject, we get 10 over 3 t cubed plus 10e to the 0.2t minus 10. Now I can find the speed of p when t equals 2 just by substituting in a 2 here. And that gives me the decimal answer, 31.6 meters per second to 3 significant figures. So that is part A. Part B, we need the distance OP when t is equal to 3. So now if I want a distance, I can remember that v is equal to dx by dt and integrate again. So for part B, we have x is equal to the integral of 10 over 3 t cubed plus 10e to the 0.2t minus 10 dt. And that gives me 10 t to the 4 over 12 plus 50 e to the 0.2t minus 10t plus c. And again, boundary conditions, when t is 0, p is at rest and it is at O, where x is equal to 0. So t equals 0 when x equals 0, but again that doesn't mean c is 0 because of this exponent here. That means c is minus 50. If you put those boundary conditions in, c is minus 50. So our final equation for x is 5t to the 4 over 6 plus 50e to the 0.2t minus 10t minus 50. And when t equals 3, that gives me x is equal to 78.6 meters to 3 significant figures. Example number 2. A rock of mass 0.2 kilograms is moving on a smooth horizontal sheet of ice at time t seconds, where t is greater than or equal to 0. A horizontal force of magnitude this and constant direction acts on the rock. When t is 0, the rock is moving in the same direction as the force and has speed 6 meters per second. When t is equal to capital T, the rock has speed 36 meters per second. Calculate capital T. So again, we've got f is equal to a function of time, 2t squared, and we know f is equal to ma, and we can replace a with dv by dt. Before we integrate, I'm going to change that to 10t squared is equal to dv by dt. So when we integrate, we get 10 over 3 t cubed plus c is equal to v. And we're told when t is 0, v is 6. So there are my boundary conditions. Put those in, and we get c is equal to 6. So our function for v is 10 over 3 t cubed plus 6. And now we're ready to find capital T when v is 36, just by putting that in. So that gives me 30, 90, 10t cubed, so t cubed is equal to 9, t is equal to the cube root of 9, which is 2.08 seconds to 3 significant figures. I suppose once I put v is 36 in there, that should have been capital T, shouldn't it? To match the notation that they've used. Example number 3. A particle P of mass 1.5 kilograms is moving in a straight line. The force acting on P has magnitude this, newtons, where x meters is the distance OP, and acts in the direction OP. So here we have our first force in terms of distance or displacement x instead of time. When p passes through O, that's x equals 0, its speed is 4. Calculate the speed of p when x equals 2. So we've got something very similar here, but now it's a distance or a displacement that we're using. So when we do f is equal to ma, our acceleration is more likely to be useful as v dv by dx. And over here we've got 8 minus 2 cos x. So when we separate the variables, we can integrate still. So the integral of 8 minus 2 cos x, if we put in the mass, that's 1.5 v dv. So on the left we get 8x minus 2 sine x plus c is equal to 1.5 v squared over 2. Now we put in our boundary conditions. V is 4 when x is 0. Putting those in, we get 0 plus c is equal to 12. So that's 3 over 4 v squared is equal to 8x minus 2 sine x plus 12. And what we need to find is the speed of p when x equals 2. So putting x equals 2 into there now should give us that. Remembering to use radians for your sign here. That gives the decimal answer 26.18 ... Timesing that by 4 over 3 and square rooting gives me an answer for v of 5.91 meters per second to 3 significant figures. Final example. A stone S of mass 0.5 kilograms is moving in a straight line on a smooth horizontal floor. When S is a distance x from a fixed point on the line A, a force of magnitude this acts on S in the direction AS. Given that S passes through A with speed 2 meters per second, calculate these two things here. This is very similar. Everything's happening in the same direction. We have force as a function of x, the distance, and a boundary condition here that when S passes through A, that's x equals 0, the speed is 2. So let me clear this up here. This is telling us x equals 0, v equals 2, that's a boundary condition there, and we're told f is equal to 5 plus 7 cos x. Of course we know f is equal to ma as well, where a here I'm going to change into v dv by dx, because our force is a function of x and not t. Doing what we did before then, 0.5 for the mass, then separating the variables and integrating gives 5x plus 7 sine x plus c is equal to 1/4 v squared. Now we can put in our boundary conditions to find c. That gives us 0 plus c on the left and a 1 on the right. So if I put that in and multiply everything by 4 just to get rid of that fraction, we get v squared is equal to 20x plus 28 sine x plus the 1 for c times 4 plus 4. Now what do we need to find? We need to find the speed of s as it passes through the point B where x is equal to 3. So we just need to put x equals 3 into this equation. Again, remembering the sine 3 is in radians there. And square rooting all of that gives 8.24 meters per second to 3 significant figures. Part B asks for the work done by the force in moving S from A to B. Now if you cast your mind back, I hope you remember that the work done is equal to the change in kinetic energy. We know the speed at the beginning is 2 meters per second, so we can work out the kinetic energy there. And we know the speed here at B is this, we can work out the kinetic energy here. So the work done is equal to a half mv squared minus a half m, let me call that v naught squared, the speed at the beginning. So a half times a half for the mass, times 8.24, but of course I won't use that rounded number, I will use the original number on my calculator, minus a half times the mass times the speed at A, which was 2. and all of that gives me 15.987 ... to 3 significant figures, 16.0 joules of energy for the work done. And there we go. I hope that's enough now for you to have a go at the questions in exercise 3A, and maybe I'll see you for Newton's law of gravitation in video 2.